An unexpected finding has been discovered tight at the edge of the world. Aren't you curious to find out what this shocking discovery might be? While using Hubble, the first optical telescope in space, astronomers have found something rare and out of the blue. The name of this team is Supernova H0, for the equation of state, which Dr. Reiss heads. Over the years, researchers have used Hubble to calculate the universe's expansion rate. The calculations have been precise and accurate since the first calculation was made over 100 years ago. The recent results derived during the calculation of expansion rate have led to a rumble amongst astronomers. What did they find out? It was discovered that the universe's expansion rate is increasing faster than the predictions made from the trajectory after the Big Bang. This has made the researchers conclude that something uncertain is at work in the universe. Reiss, the head researcher of the team, mentioned that the team has been struggling to dissect what this unusual finding means. NASA has made it known that if the expansion rate slows down, it means there is something in the universe leading to that. And also, if the expansion goes faster, it could be dark matter pushing the expansion growth faster. For about 6 years, Reiss, a Nobel laureate who works in the Space Telescope Science Institute and Johns Hopkins University, both in Baltimore, Maryland, and his team used the Hubble telescope to refine the measurements of distances between galaxies. The stars of these galaxies were used to mark the mileposts. Whatever measures they gathered are used in calculating the Hubble constant. And what is the Hubble constant? The Hubble constant is simply the measurement unit used to describe the universe's expansion. The constant was first proposed by Edwin Hubble, who specializes in studying galaxies and their distances. More importantly, those far away from our planet. Earlier on, it was discovered by Hubble in 1929 that galaxies move away from each other, and the faster they are from Earth, the faster they move. Then, it was all considered as galaxies moving away from each other, but now researchers understand that it is the expansion of the universe. The study made by Reiss and his team shows that the distances between the number of stars analyzed are up to 10 times farther into space, unlike the previous findings by Hubble. The Planck satellite, owned by the European Space Agency, after observing the Big Bang, predicted the expected values. Planck satellite predicted that the Hubble constant value should be 67 kilometers per second per megaparsec, and could be no higher than 69 kilometers per second per megaparsec, which means for every galaxy that is 3.3 million light-years farther away from us, it is moving at a distance of 67 kilometers per second faster. The team, however, measured a value of 73 kilometers per second per megaparsec, with a 9% difference from its first predicted value. This shows that the galaxies are moving at a highly faster rate than the constant value first proposed after the Big Bang. One could wonder if the Hubble telescope has made a mistake or is faulty, but Reiss dismisses this by saying both results have been tested multiple ways, so barring a series of unrelated mistakes, it is increasingly likely that this is not a bug but a feature of the universe. Data recorded by Hubble is always precise, and astronomers cannot but take the gap in the measurements seriously. In further explanations made by the team, Reiss enlists some reasons why the universe could be expanding and changing the contents of the early universe, which all relate to the 95% invisible parts of the universe filled with dark matter, dark energy, and dark radiation. The first reason is related to dark energy. Dark energy accelerates the cosmos and could be capable of moving the galaxies away from each other with even greater strength. That is, acceleration might change over time in the universe and might not have a constant value. The second reason is the possible interaction of dark matter with another stronger matter or radiation. Another possibility is that the universe contains new subatomic particles traveling very close to the speed of light. These fast subatomic particles are called dark radiation, and they consist of known particles like neutrinos that are created during radioactive decay and nuclear reactions. These new particles are called sterile neutrinos that can only be affected by gravity, not subatomic force, like other regular neutrinos. There are currently no direct answers to the causes of these fast expansion rates, but the team has been working to ensure the measurements and calculations made by the Hubble Space Telescope are more precise. Reiss and the team have been on a journey of refining Hubble to a better, easy-to-understand, and implementable precision. So far, they have been able to decrease the uncertainty in measurements to 2.3%. Recently, the team has been building a strong cosmic distance ladder. Researchers use the cosmic distance ladder to measure the accurate distance to galaxies far and near the Earth. The distances are then compared with the expansion of space as measured by stretching light from receding galaxies, after which they calculate the Hubble constant with the apparent outward velocity of galaxies at each distance. Because the Hubble constant value is as precise as the accuracy of measurements, astronomers have resorted to using special stars and supernova as cosmic yardsticks or milepost markers to precisely measure galactic distances. The Cepheid variables are the most reliable set of stars for measuring shorter start distances. In 1913, Henrietta Leavitt, an astronomer, was the first to determine the usefulness of the Cepheid variables in measuring distances. While using the Cepheid variables, a parallax is used to measure the distances to Cepheid without their brightness. The parallax is the difference in the direction of a celestial object as seen by an observer from two widely separated points. The ancient Greeks discovered the technique as they studied the distance from the Earth to the Moon. The latest Hubble result is based on measurements of the parallax of 8 newly analyzed Cepheids in our Milky Way galaxy. These stars are about 10 times farther away than any studied previously, residing between 6,000 light-years and 12,000 light-years from Earth, making them more challenging to measure. Observations made while using Hubble in the past show that 10 faster blinking Cepheids are located 300 light-years to 1,600 light-years from Earth. For measuring parallax with Hubble, the apparent tiny wobble of the Cepheids due to Earth's motion around the Sun is gauged by the team. The size of the wobbles is about 1/100th of a single pixel of the Hubble Space Telescope. For accurate measurements, the team invited a new scanning method. Using this method, Hubble measures the position of a star 1,000 times a minute every 6 months for 4 years. They also compared the brightness of the Cepheids and supernova in those galaxies with better confidence, so they can more accurately measure the star's true brightness and therefore calculate distances to hundreds of supernova and far-flung galaxies with more precision. While using this new method, Reiss says, this method allows for repeated opportunities to measure the extremely tiny displacements due to parallax. You are measuring the separation between two stars, not just in one place on the camera, but over and over thousands of times, reducing the errors in measurement. The brilliant thing about the new studies and improvements the team has made is that they used the Wide Field Camera 3 in Hubble to calibrate the luminosity of Cepheids near the Earth and in faraway galaxies. By doing so, they have removed the systematic errors that are oftentimes introduced while comparing measurements from various telescopes. As mentioned earlier, the team's main goal is to continue reducing uncertainty while measuring the distance and position of stars. How do you feel about discovering that our universe is expanding? What do you think about the improvements being made by the Supernova H0 for the equation of state team to the Hubble Space Telescope for more precise measurements? Share your thoughts in the comments section. We absolutely can't wait to hear from you.